All right, we are live. So I guess I think we can start the presentation and uh, people will join soon. Cool. Let me share my screen. So it's I am audible and it's full screen just to confirm.
Yeah, it's good.
Awesome. So thanks everyone for joining this workshop, and we are really excited to share a lot of our learnings in past years about machine learning models, the creative applications, and a lot of possibilities which through these models you can integrate in your workflow. And I started my journey of learning machine learning last year through Digital Futures Workshop, and I'll be sharing some of those explorations with you soon. But the key goal, if I were to say for this workshop, is just have fun. And like there are so many things which once you start experimenting with these models, you will realize the creativeness and novelty you'll get through these models. So feel free to like play around with the images, play with the input query, and there are like a lot of things people discover by experimenting. So the goal is first uh, experimenting a lot, and second is like understanding the technical details, because I feel that once you get start having fun with AI, that internal motivation will lead you to like learn more about the technical details and do more courses. So yeah, I'll start with a brief intro of myself. So I am a master's in architecture student from University of Illinois. I did my bachelor's in civil engineering from IIT Bombay, and then I worked as a structural engineer at Bureau Happold Engineering. My key interests are machine learning applications in AEC, along with blockchain and creative coding. And I also run a YouTube channel called Engineering Architecture, where I share my learnings, do machine learning paper review, host amazing people. And I just like sharing knowledge and awareness with the community. And there is a very bright future and possibilities of AI in AC, and I can't wait to develop some amazing tools. Daniel, would you like to jump in?
Sure. My name is Daniel Escobar. I have a background in architecture, and I work currently as an architectural designer in New York. But I also got interested in machine learning a while ago when I attended a smart geometry workshop, and got exposed to some of the things that architecture designers and engineers were doing with machine learning. So that got me really interested, and then I pursued a master's of computer science with a focus in machine learning to understand more of the mechanics and the technical aspects of it, and why it actually works, and what are some of the limitations inherent in some of those algorithms. And then after sort of going through that and learn a little bit more how they work, I started looking more into ways of how they apply to architectural design and how they can be used either in a creative, generative way or through some other methods that are more pragmatic. But my most, I guess, most interesting part about it is how you can use them in collaboration. So, like, if you're a designer and you're developing ideas, like, how can you use this technology, which in some ways it needs a lot of data, but it allows you to explore new ways. It might provide you with new ideas in the process. And that's sort of like the experience that I have with machine learning, or that's kind of what excites me about it, is like you can collaborate with it to develop like new novel things. So that's a little bit about me.
And one thing which we would like in this workshop is feel free to interrupt us and make it as interactive as you can, because like I feel like I met Daniel in one of the workshops in social algorithms, and then we met frequently in other architectural technology workshops, and that's how like you make friends and you collaborate with each other. So like feel free to make like best use of this opportunity to meet other like-minded people. So I'll give you a brief overview about this workshop. So we have like uh, two parts in for each session. One part is theory, and another part is hands-on experimentation. And at the end of each day, we have like fun experiment exercises for you guys. So day one today will cover what Daniel will be presenting about intro to AI and architectural design applications, and he'll cover like very high level overview about different machine learning models, different kinds of learnings. I'll be giving hands-on tutorial about style transfer, and at the end for tomorrow, the exercise which will be due is what are three design themes you want to explore with AI, and sharing 10 best style transfer results with us. And I'll cover that later, how and where you need to upload. So tomorrow we have invited Pedro Veloso for to give a guest lecture on generative design applications with AI. And after that 30-minute lecture, I'll be covering the basics of clip model and GAN. And after that 1 hour theory part, we'll have like 30 minutes of students Q&A about uh, yesterday's work, and also we'll do like 2 minutes per student quick presentation of what are some results they got and some findings. Then Daniel will be giving hands-on collab tutorial on using clip, and for that day the fun experiment exercises exploring a lot of images with clip and sharing the top 10 results with us. On third day, Daniel will be giving theory explanation about how multimodal AI works, how clip and VQ can be combined to create amazing AI artwork. And then after that, I'll be giving some hands-on tutorial about how to use clip and VQ can. Once you know that script, you will be able to create like walkthrough videos just through text. And I'll be showing few examples like what those results look like. So at the end, on fourth day, what you will have is from day one using style transfer, you'll realize what kind of texture aligns with your input desire. Because sometimes, let's say if you want to make abstract art or abstract architecture, there are few images which work better with your building in hand and few which won't. And it's very subjective and it depends on your ultimate desire. From day two, you will, after your experimentation, you will realize that based on the input image you give, how clip interprets the image and give like description of that image, and you'll see different kind of uh, description in the training process. And the reason that's important because on third day we will be doing text to image and text to video generation. So if you know how clip works and how what kind of uh, text description clip gives, it will help you to experiment better and get better understanding with when you're working with clip plus VQGAN models. And at the end, it's very open. Like you could maybe design a whole space with AI using these models. So day one is like image to image translation, day two is image to text translation, and day three is text to image translation. So let me show you like what the results look. So for example, day one experiment is like working with StyleGAN. So you can take any input image, have another style image which you want to transfer on the content image, and then you'll produce like a stylized image. So you can work with circuits, you can work with buildings, you can work with furniture. Like the scale is very open. There are interesting things you will find out. Day two is you'll do like input image, and then from the training it will show you the title, like the text description. And this is like one showpiece like where I just inputted like a walkthrough through art gallery in contemporary modern style, and you can see how the model is traversing through the space. So you can literally do like zoom in, panning, a lot of different things with this model. So the ultimate aim is, apart from fun experiments, if you are interested, you could create like a architectural experience through a building, through a urban park, or maybe at furniture scale. So that's why on day one we are asking you to present like 3 design theme ideas you want to explore through this workshop. We have a Discord link which we are asking you to present like the top 10 results, but there might be like some interesting failures or interesting findings you will have during this whole process. So feel free to share your work in the Discord channel. And the aim of uh, requesting you to present work each day is a lot of things can be learned from other people. Like, for example, a particular texture worked well compared to other texture for someone, and you can learn from, okay, why not I can use that texture in my work and maybe uh, work around it. So now I'll hand over to Daniel.
Mary, do you want to like have the students do like a quick introduction of themselves, just so like everybody kind of knows like where they're coming from and like what their interests are, and maybe like if they can say more or less like how familiar they are with machine learning, like I guess like what level of understanding, and yeah, just a brief introduction would be great.
I totally forgot about that. Let's do this thing like uh, name, where are you from, what's your current like education or work profile, and what are your expectations from this workshop and current exposure to AI.
Sure. So if anybody wants to go first.
I can go first. Hi, and sorry for my voice because it's too early in my country. It's 5 a.m. I'm Sıla Kartal, and I'm currently studying my master's degree in Bilkent University through the field of architecture, and I'm also studying artificial intelligence in architecture and how can we produce floor plans. But I'm just familiar with the theory part of this, and I hope this workshop will boost me about starting a hands-on process. Thank you.
Thank you.
Great, thank you.
Right. I'm going to introduce myself. I am Ricardo from Brazil. I am also a Master of Science student at London State University. And I am also I'm working with pix-to-pix models to design floor plans as well with semantic segmentation. I've already trained just like a STYLEGAN model to design chairs. I've already trained the CycleGAN models, but there's always something new to learn, you know? Every day there comes a new model and new stuff going on, and we always have to like keep researching to keep updated because it's kind of impossible, but it's very fun to do it, and I like so much.
Awesome, thank you.
Awesome.
This is Harish Karthik. I'm right now in my undergrad architecture. I'm from India. I'm an absolute beginner to AI. I have read about the theories that go behind machine learning models, but I've never tried out anything hands-on. So I guess I'm gonna make some new friends who are into AI, who have already done a lot of AI, and I'm really eager to learn a lot from you guys. Thanks for the workshop.
Thanks for
Thank you
joining.
for attending.
Hi everyone, my name is Yan Zhao. I usually go by Anthony. I'm currently studying a Master of Architecture in Rhode Island School of Design. I don't think I have any experience with AI. That's why I'm like signing for the introduction for AI for this course. And I'm looking forward to learn a lot from you too. Thank you.
Thank
Thank
you.
you. Anyone else?
Should I pick someone or I don't know?
Hello, I'm Ashraqat Khalid. I'm from Egypt, but currently I live in Abu Dhabi. So I finished my bachelor degree in architecture in Egypt in MSA University, and I'm still not certain which field in architecture to go through. So when I found the AI workshop, I was really interested to join and to know more about it. It might be my concern later on or something like that. And yeah, it's also here, it's in the morning, it's 6 a.m. in Abu Dhabi. So yeah, thank you.
Yeah.
Awesome. Thank you.
Thank you. Yeah, it means a lot. Like you guys are at some places it's late night, some places to early morning. So thanks for joining.
Yes.
If you're facing any issues with mic, feel free. You can also share in the chat. Anyone else who? Right.
All right.
Can maybe start, and when they are comfortable,
All right.
they can. Yep.
All right. So I'm gonna start with just kind of like a overview of I guess machine learning and some of the typical algorithms that are being used, and then I'll follow that with some examples that people have been doing, let's say, like more of a design-oriented way. So I think that should be helpful to sort of see like a broader picture of what's out there, maybe provide you with some ideas later on. So I'll get started. Let me share my screen. All right, so let me know if you guys see it. Good.
Yep.
Okay. Okay, so I'll start. So I'm just gonna start with what is AI? So artificial intelligence. So Oxford Dictionary defines artificial intelligence as the ability to acquire and apply knowledge and skills. And in our case, we want to use machines to make decisions based on their learned knowledge. So there's like a process to it, and there's essentially three parts. There's like perception, which is observations of the environment. So how do we take in, let's say, data from the environment? And there's the learning process, which is how do you process those observations to essentially understand any patterns that allow you to make some sort of boundary decision on that knowledge. And that leads to basically, once you understand the data, then you can take a decision or you can act on that knowledge. So that's in a broader sense that encapsulate what artificial intelligence is. And then we can compare that to human intelligence, which is kind of the overall goal of this field. So for perception, so what types of environments are we taking data from? So one of them is like vision. We can see either through images or through videos. Another one is audio. So this is music, conversations, or any sort of anything that falls under this category. And then data. And data is like a more broader thing because you could take, for example, something like likes on an image or financial transactions or just like emails or any sort of data that can be processed and collected in some sort of manner on the computer. Learning. So what do? We essentially take that data and feed it into some algorithm, and it's gonna find some sort of pattern. So that's kind of the purpose of learning, to be able to understand and learn patterns. And these patterns can either be repeatable or sometimes we use them to see if there's some anomalies. So if something stands out as different. And decisions. So once we have that data, we can take that data and essentially delineate whether there's some boundaries. So we could say, oh, this leans more towards yes, this leans more towards no, and we can then take a decision based on that. So artificial intelligence, it's sort of like let's say the broader picture. Machine learning is a subset of that, and machine learning is basically the use of statistics and math to process data to learn these patterns. Deep learning is a subset of machine learning, which uses what are known as like multi-layers or deep neural networks. And essentially, this kind of takes off more recently since we have more data to process and more computational power that deep learning really is able to process, and essentially through developing these new architectures that grow in like the number of layers, it can learn to understand more patterns. And the types of machine learning that are common, it's split into three parts now. You have supervised learning, unsupervised learning, and then reinforcement learning. And as more recently, there's been also a focus into methods of self-supervision. One of the issues for that is because supervised learning requires a lot of labeled data. And if you have worked with some of these algorithms, if you want to train them and you want to use a supervised method, it takes a lot of effort to label the data. So as of recently, there's been more exploration and research into how can you take what's available and develop some sort of method to use that data to supervise itself to generate sort of like those predictions or the categories. So this is something that a lot of top researchers are looking towards developing, because that would open, let's say, the field to a broader aspect. So I will start with supervised learning. So basically, supervised learning has two types of categories, and one of them is classification, and the other one is regression. In supervised learning, you have the data X, and then Y, it's sort of like the label or the category. And you can either divide these data points, and then you can distinguish if it's like a cat, a dog, or if it's like a book or a cell phone. So that would fall under classification. Regression applies more to the prediction of numbers. So if it's like a continuous number, so let's say you want to predict the price on like houses using real estate data, that would be more of a regression problem, since it doesn't have a clear category. It's more about predicting some sort of number. Unsupervised learning can essentially fall into two categories. One of them is dimensionality reduction. And with unsupervised learning, we're not given the label data. So we're given just the data itself, and we apply some algorithms in order to have them define where the data falls under. And one example is clustering. So you can see here that if you have a whole bunch of data points, they essentially begin to cluster around similar data points. And another aspect, the other aspect is dimensionality reduction, which pretty much allows you to compress the knowledge of all those data points and explains it, for example, in two features. So that's another aspect of it.
Hey, Daniel.
Yeah.
Can you also like share real life examples of like those algorithms so we can understand like the applications as well?
Yeah, I will show them after this. I'm just giving like kind of overall of the supervised, but I'll show examples in the next section. And then reinforcement learning is it's different than supervised and and unsupervised learning in the sense that you have an agent, and this agent is taking an action in the environment, and then it's taking an observation in that environment and sort of calculating a reward based on that action. And through those steps, it allows them through time to essentially learn what are the best actions to take. And okay, so now that's kind of like an overall view. Does anybody have any questions?
Yeah, and there is nothing called ceiling questions, so feel free to.
Not yet, I guess.
Okay, all right. So I'm gonna talk about like so I just gave an overview, kind of like what are the different types of algorithms and what categories they fall under, and more or less like what they're doing. Now I'm gonna talk about like what do you feed into them? What are the data representations that actually you're gonna process to learn some pattern out of it? So what is a representation? So the description or portrayal of something in a particular way or as being of a certain nature. So this is more or less like what are the, how do we take an image or something and encapsulate it into features that represent the object? So for example, here, this is vision. So some of the types of data and uses for vision, we can take images, and they usually come in RGB. So they have like the 3 channels. And RGB just stands for like red, green, and blue. And some of the things that we can do with these images, or we can apply algorithms, is to find the object, so object classification. So what type of object is this? Object segmentation, to separate the object from either the background or from other objects. Object localization, so where is the object located in the image? Prediction of movement, so this applies more if you now take a series of images, like for example, a video, and you can essentially predict, let's say, where a person might be moving. So this is helpful, for example, in computer vision for automated driving. And then image generation, where we sort of take, let's say, a data set of images, feed into a generative algorithm, and generate a new synthetic data set of images based on the images that it's seen. For text, we can use text, and this comes kind of like, you can get it from anywhere, like text, Wikipedia, Twitter, you can train models on this data. But the way that was interesting about text is that text gets encoded with numbers as well. So instead of like with images, you have kind of like a image of 256 by 256 pixels. With text, you're encoding kind of like let's say like the words by a number. So each word, it represents one number, and this is how the algorithm gets fed. And we can take this text now and process it, and we can use it for machine translation. So from one language to another language, we can use it for sentiment analysis. So if we want to classify the text, if it's like good or bad, like for reviews on websites or things of that nature. We can also use it for information extraction. So if you want to read an article, maybe like a financial advisor or like an investment bank, they want to take articles from financial reports and then extract important information out of it. We can also use it for question and answering. So if you provide a question, it should be able to answer relevant information about that question. Text categorization, so whether the text is of a certain noun, a person, a thing, or it's like somebody famous. Connection analysis, so like if you want to connect people in a text to other people and how they're related to each other. And then summarizing. Summarizing is similar to information extraction. So if you want to take a large body of text and pretty much provide a summary of the whole text. Next is 3D data. And this, I think, is more interesting to us as like architects and designers. So 3D data comes in several representations. There's Euclidean structured data, which it can be voxels or points in space. And then you have non-Euclidean data, which is like graphs and meshes. And we usually work with these either like in 3D software or even like AR, VR. And this type of data can be used for classification. So you can classify objects or you can classify parts of an object. Segmentation, which that's also like classifying a certain part of an object. Object recognition. You can also do reconstruction. For example, if you have a point cloud and you want to reconstruct it as a mesh. Generation, so you can generate an object. AR and VR, so this is essentially a lot of new uses that have come into play where like now you can use generation and you can place somebody in an AR VR environment and recreate the scene around it. And then data compression, so how do you want to encode all these let's say point clouds into one representation, or all these graphs and meshes into one representation. And this is useful because like if you have worked with design software, sometimes models can become quite computational intensive. So this is a good way to reduce that. Audio, you can also encode audio, and it works more like a time series. And you can use it for classification, reconstruction, and generation. Temporal series, this is similar to audio in the sense that it's also a time series, but you can use it, for example, for financial data or other sort of things that rely on a time. And you can use this for prediction, let's say, of a certain a time step. So for example, if you want to take the price of like this stock and you want to like predict what is like going to be the price in the next month, you can use it for something like that. You can also use it for anomaly detection. So if there's like a certain time series and you want to take a look at it, you want to see like where are the weird or different things that are occurring that are not common to like to say the inherent pattern. Graphs, so graphs are also useful. They are being they have like a lot of use now, especially with proteins and things related to developing vaccines. Essentially, graphs is just a connection between nodes and edges. A graph can also be a representation of a mesh. And you can use this type of data to predict nodes, categorize nodes, reconstruct, and then predict the connection between the nodes. Does anybody have any questions now?
Daniel, maybe
Yeah.
can you clarify, like how different types of data are fed into the neural network, like because it's just numbers, so how the conversion happens.
Okay, sure. Um, so let me see if I can. All right. All right. So I'll just
Or
go
maybe
over
you
that.
can just continue. Sorry, maybe
Yeah.
it will be easier. Yeah.
Yeah, I'll just show you. I'll talk about it like when I run through the algos because they work differently in some. So I'll explain that a little bit. So now I'll talk about like the different types of algorithms. So what is an algorithm? It's a procedure to solve a mathematical problem in a number of steps that frequently requires the repetition of a function in general terms. So this is what they call the deep learning model zoo, and you have different types of algorithms for different purposes. So you have the CNNs, which are the convolutional neural nets. You have the GNNs, which are graph neural networks, RNNs, recurrent neural networks, transformers, and deep sets. So all these algorithms use this basic function in order to work, or in order to be able to learn and understand the patterns. It's called the backpropagation function. And essentially what the backpropagation function does is that it takes the inputs, runs some sort of, let's say, functions, a mathematical function, outputs a prediction. It takes that prediction and calculates the difference between the prediction and the ground truth, or the actual real output input, and then it calculates that error and then sends it back. And then when it sends it back, it updates the weights in the algorithm, and it modifies the weights in a certain way that every time that it runs this operation, essentially what it's trying to do is to diminish the difference between the prediction and the ground truth. And when it diminishes enough, then it's able to predict pretty accurately on unseen data, or at least that's sort of the intuition behind it. So one of the most basic algorithms is the multi-layer perceptron. And the multi-layer perceptron, essentially you input in your features, which is this part here. So you can input features, for example, of image of a dog. And in this case, the input for this could be like a matrix of an image. So a matrix would just be like a 256 by 256 image of a dog. And you can send that into the network here. And it contains hidden layers. The hidden layers are usually, let's say, some mathematical functions that calculate some weights. And after it passes through this function, it generates an output or a prediction that gets outputted and then sent back through backpropagation once it calculates the error and then changes the weights again. So you run this process over and over again with different variety of, let's say, images, until it's able to recognize like what's a dog and what's a cat. Recurrent neural networks are essentially taking that multi-layer perceptron, and instead of just being one multi-layer perceptron, it's sort of running a loop in time. So it's the same multi-layer perceptron, but it gets updated in time step. So you feed in, for example, let's say image, and then it goes in one time step. So this actually works well for like videos, for example. If you have a series of images, so at each time step, you're feeding in a new image or a frame of a video, and then it generates some sort of prediction on that. So that's how recurrent neural networks work. They're multi-layer perceptrons, so they can be adapted to use other architectures, but they work as in time steps. And now this is the convolutional neural network. And convolutional neural network, the way that it works is that it takes an input, let's say an image of 512 by 512 times 3, and 3 is the, let's say, the channel, so RGB, and it runs a sort of window across it. And this window, what it's doing, is calculating or extracting, let's say, some features from it and sending them out through a compression time mechanism or a function where it sort of takes the features and compresses them more and more and more to finally generate some sort of prediction on that. And this one can be used for a variety of things. You can use it for classification or other sort of things. But the main part about it is that it runs a sort of filter window across an image to extract the features. Transformers. Transformers are a method of deep learning that takes a new approach. It's similar to a recurrent neural network, is that it processes like a time series, but what it does is that it uses attention mechanism, and attention mechanism allows it to have like infinite time sequences because it allows it to focus on the parts that are most relevant. Let's say, for example, you take a sentence, it allows it to sort of find some sort of correlations between the words and the sentences as it reads through the sentence, and it can keep going and forming an understanding of what, let's say, a whole paragraph says. Vision transformers are also a modification of the original transformers that are now being used for vision tasks. So they can be used also similar to like a CNN for classification in the same way. So I was going to show this video that kind of explains transformers a bit, and transformers are important because for our what we propose for the workshop, we're going to use VQGAN and CLIP, and both of these architectures, they use the transformer architecture in order to encode, let's say, like the images and to encode text. ¿Se escucha? Mary, you can't hear it?
No. I was just about to say that.
Oh, okay.
You might need to reshare and enable sound.
Okay. Sorry.
No problem.
What is it over here?
While you can, you might need to unshare it, and while resharing, there is an option of enable sound.
Oh, okay, gotcha.
Its own sci-fi novel. Mechanism, let's start with a fun text generation model that's capable of writing its own sci-fi novel.
Yep.
Now, Norley.
Okay.
We'll need to prime the model with an arbitrary input, and the model will generate the rest. Okay, let's make the story interesting. As aliens entered our planet and began to colonize Earth, a certain group of extraterrestrials began to manipulate our society through their influence of a certain number of the elite of the country to keep an iron grip over the populace. By the way, I didn't just make this up. This was actually generated by OpenAI's GPT-2 transformer model. Shout out to Hugging Face for an awesome interface to play with. I'll provide a link in the description. Okay, so the model is a little dark, but what's interesting is how it works. As the model generates text word by word, it has the ability to reference or attend to words that is relevant to the generated word. How the model knows which word to attend to is all learned while training with backpropagation. RNNs are also capable of looking at previous inputs too, but the power of the attention mechanism is that it doesn't suffer from short-term memory. RNNs have a shorter window to reference from, so when the story gets longer, RNNs can't access word generated earlier in the sequence. This is still true for GRUs and LSTMs, although they do have a bigger capacity to achieve longer-term memory, therefore having a longer window to reference from. The attention mechanism, in theory, and given enough compute resources, have an infinite window to reference from, therefore being capable of using the entire context of the story while generating the text. This power was demonstrated in the paper Attention is All You Need, where the authors introduced a new novel neural network called the Transformers, which is an attention-based encoder-decoder type architecture. On a high level, the encoder maps an input sequence into an abstract continuous representation that holds all the learned information of that input. The decoder then takes that continuous representation and step by step generates a single output while also being fed the previous output. Let's walk through an example. The Attention is All You Need paper applied the transformer model on a neural machine translation problem. Our demonstration of the transformer model would be a conversational chatbot. The example would take in an input text, "Hi, how are you?" and generate the response, "I am fine." Let's break down the mechanics of the network step by step. The first step is feeding our input into a word embedding layer. A word embedding layer can be thought of as a lookup table to grab a learned vector representation of each word. Neural networks learn through numbers, so each word maps to a vector with continuous values to represent that word. Next step is to inject positional information into the embeddings. Because a transformer encoder has no recurrence like recurrent neural networks, we must add information about the positions into the input embeddings. This is done using positional encoding. The authors came up with a clever trick using sine and cosine functions. We won't go into the mathematical details of the positional encodings in this video, but here are the basics. For every odd time step, create a vector using the cosine function. For every even time step, create a vector using the sine function. Then add those vectors to their corresponding embedding vector. This successfully gives the network information on the positions of each vector. The sine and cosine functions were chosen in tandem because they have linear properties the model can easily learn to attend to. Now we have the encoder layer. The encoder layer's job is to map all input sequence into an abstract continuous representation that holds the learned information for that entire sequence. It contains two submodules, multi-headed attention followed by a fully connected network. There are also residual connections around each of the two submodules, followed by a layer normalization. To break this down, let's look at the multi-headed attention module. Multi-headed attention in the encoder applies a specific attention mechanism called self-attention. Self-attention allows the model to associate each individual word in the input to other words in the input. So in our example, it's possible that our model can learn to associate the word you with how and are. It's also possible that the model learns that words structured in this pattern are typically a question, so respond appropriately. To achieve self-attention, we feed the input into three distinct fully connected layers to create the query, key, and value vectors. What are these vectors exactly? I found a good explanation on Stack Exchange stating, the query, key, and value concept comes from the retrieval system. For example, when you type a query to search for some video on YouTube, the search engine will map your query against a set of keys, for example, video title, description, etc., associated with candidate videos in the database, then present you with the best match video. Let's see how this relates to self-attention. The queries and keys undergoes a dot product matrix multiplication to produce a score matrix. The score matrix determines how much focus should a word be put on other words. So each word will have a score that corresponds to other words in the time step. The higher the score, the more the focus. This is how queries are mapped to keys. Then the scores get scaled down by getting divided by the square root of the dimension of the queries and the keys. This is to allow for more stable gradients, as multiplying values can have exploding effects. Next, you take the softmax of the scaled score to get the attention weights, which gives you probability values between 0 and 1. By doing the softmax, the higher scores get heightened and the lower scores are depressed. This allows the model to be more confident on which words to attend to. Then you take the attention weights and multiply it by your value vector to get an output vector. The higher softmax scores will keep the value of the words the model learned is more important. The lower scores will drown out the irrelevant words. You feed the output vector into a linear layer to process. To make this a multi-headed attention computation, you need to split the query, key, and value into n vectors before applying self-attention. The split vectors then goes through the same self-attention process individually. Each self-attention process is called a head. Each head produces an output vector that gets concatenated into a single vector before going through the final linear layer. In theory, each head would learn something different, therefore giving the encoder model more representation power. Okay, so that's multi-headed attention. To sum it up, multi-headed attention is a module in a transformer network that computes the attention weights for the input and produces an output vector with encoded information on how each word should attend to all other words in the sequence. Next step.
Okay, so I'll stop it there. But that was the main sort of aspect of why transformers work, and that was essentially what we're gonna do in the workshop. What the clip model and the VQ GAN, how they employ this sort of attention mechanism to generate, let's say, new images and text. I'm gonna move on to some other networks, and then I'll run to like samples of design work using neural networks. So this one is the graph convolutional network, and it takes as a representation graphs, and you can encode a graph to feed into a network into an adjacency matrix. An adjacency matrix would be similar to an image representation, like say, for example, of 256 by 256. And then you feed it to graph convolution to generate some sort of prediction. And then another network that's fairly popular for its generative nature is the generative adversarial networks, or known as GANs. And these networks take noise that gets fed to a generator. This noise is then fed into a discriminator alongside with the real data. And then the discriminator needs to learn in a sort of adversarial way, whether if the image generated by the noise is a real image or a fake image. And once it sort of learns that, then it's able to get the generator to produce images that look more and more like the real data. Yeah.
I'm not sure, but I'm like hearing like the notification of Discord in the background. Is it from you or other? I'm not sure.
Hold on one second. Let me... Okay.
Thank you. Yeah.
Sorry. Okay, so one of these types of generated networks is the pix-to-pix. Oh, it's still mine. Sorry. Okay. One of these types of generated networks is the pix-to-pix, which maps, let's say, one domain to another domain, but there's some limitations to pix-to-pix in that you have to have sort of like a fairly one-to-one representation if you want to use it. So if you feed in, sorry, man, I still hear the Discord, but I turned it off.
Oh, maybe you can turn off the sound sharing and, or it's fine. Like,
Yeah, sorry. Okay. Sorry about that. So pix to pix maps one image to another, but you have to have pair images. So they have to have the same sort of type. So if you want to have, for example, this building facade, you want to have some sort of correlation between what colors you're matching to it. And then once you train it on this, and you can generate new images. If you provide, for example, the colors, it should generate similar images like this one here. The other aspect of this, so like where Pix2Pix was constrained to having like pair images that were very similar, CycleGAN tries to get rid of that limitation by having on-pair images. And what it does is that it learns through both, through both images, it learns to predict the other one from one image, and it learns to predict the other one from the other image. And then it's able to do this and generate images that are kind of similar or that they map to one another, but they don't have to be the same image and style. So that's one of the interesting parts about CycleGAN. And then more recently, StyleGAN, which has become a fairly popular network in its ability to pretty much generate very realistic faces of people. It takes an image, it upsamples it in various, let's say, levels of resolution, and is able to understand what stylistic features map to a certain resolution. And then it sort of takes those features and injects them back in as it sort of, let's say, downsamples the learned features and generates like a new image. So all these processes are all GANs in the sense that they are all generating, let's say, they're being generated from like noise, and then that noise gets fed to a discriminator to be able to say whether it's fake or not. But they just have different, let's say, techniques or tricks in the architecture that allows it to learn the features in a more robust and expressive way. And then more recently, CLIP, which is a constructed language image pre-training model developed by OpenAI. So what's interesting about this model is that it takes text and an image in a pair way, and it encodes the text in an image. So this is where the transformer model comes in. And it's able to encode the text in a transformer model and the image as well, and develop this sort of like one-to-one relationship. And you can see kind of like on the diagonal is on the diagonal where the text and the image match up, that is usually the highest probability matching. And as it moves away from that, it should have lower probabilities because these are the less related images and text. Once you have that, then you can run an image through this image encoder, and it's able to generate a text of that image. And as of more recently, new models are being developed that are now taking this multimodal aspect and combining them with even audio. So you can take a clip model and then add audio to it, and you can run the same process to generate this pairing and be able to predict, let's say, audio or text from it. And this leads to another model recently developed by OpenAI called DALL-E, which is a generated network with text and image. So in this one now, you're taking clip and applying a generated image model. In the case of DALL-E, they use a vector quantized variational autoencoder, which is similar to GANs. but it works a little bit differently. However, it is also able to generate images. And here you can feed in the text prompt. So like if you want to say, for example, here an armchair in the shape of an avocado, it's able to generate an image based on that. On the right side is an example of somebody from Twitter who also used a similar model to this called the VQ-GAN with Clip. It works similar to DALL-E, but you can see kind of more or less the types of images that you can generate where somebody fed in the universal library and it generates this image. And another type of model that's being developed recently in order to develop a representation of more three-dimensional objects is called NERV, and that stands for Neural Rendering Radiance Fields. And what this model does is essentially it takes like a series of images and it's able to build some sort of 3D representation of the images by shooting, let's say, rays into space, and wherever these rays intersect, they output a certain probability of color and opacity. And once it learns, let's say, that feature, it's able to generate like a 3D model, and then you can run a camera around it from novel views, or let's say for camera viewpoints that that no images were taken of, and it's able to generate, let's say, new images from that. So this is really is becoming really helpful because it allows you to have a representation of a 3D object just through images, and it compresses a lot of information. The only issue with this models at the moment is that they're very computationally intensive to train, but they're making great progress in this area. So what's interesting about these types of models and, for example, photogrammetry, traditional photogrammetry, is that where photogrammetry has certain limitations, and for example, if it doesn't see a certain part of the object, it's not gonna be able to generalize or predict what might be around it. Whereas these types of models should allow for some generalization or smoothing of that unseen area. And they also are able to capture very fine detail without any limitations in geometry. And then multi-agent reinforcement learning. So this is an example developed by OpenAI of two agents playing hide and seek. So I said before, like reinforcement learning is a method where you take actions in the environment, and then based on the actions that you take, you get some sort of reward, or you observe the state that you're in, and you get a reward based on that, and you want to maximize your reward. And in this case, this is a multi-agent version of it, where these two agents are playing hide and seek, and they're trying to maximize their reward of essentially not getting caught by the other agents. And what's interesting about this is that just through that sort of mechanism of taking an action and then observing the state and then getting a reward for that, these agents develop their own sort of behaviors. And that allows them to either generate novel behaviors that maybe somebody that would program this sort of thing couldn't think of. So this is kind of fascinating that they're able to do that. And then another type of network that is becoming more popular recently is neurocellular automata. So this is your typical cellular automata, but applied to neural networks. So now you can take a neural network and have it learn like rules for cellular automata. And based on these rules, it's able to learn like complex rules and generate objects in a fairly complex way. And what's interesting about that is that since it essentially just learns rules, you can sort of in a way destroy the object and it could like regenerate. So that's what makes it like really interesting. And there's been a lot of recent work on this now and seeing how this can be applied to generate like functional machines and things like that. So you can see kind of like in this video some of the things that this group of people worked on. So what's interesting about this is like you can take, let's say this is in Minecraft, but it's able to generate like fairly complex objects just from like a few model components, and then based on some let's say rule that they want to learn, like it can generate all this just by using a neural network on cellular automata. Okay. Okay. Does anybody have any questions for Emil? All right.
I think like we are still absorbing.
Am I going too fast or am I doing all right?
No, you're doing great.
Okay. All right, so I'm just gonna now go into some samples of some architects or designers that have used neural networks in their work. And I thought these are some examples that are fairly interesting. They cover like a wide range of approaches to how to use neural networks in design work. So I'll start with this one. So the first example is this school in China by Spanarch. And what's interesting about this is that they also use text to generate like an image out of it. And in this case, they're taking text from like a poem, and they're able to generate like this sort of image that gets translated into a 3D object. And they apply some other sort of algorithm to be able to guide kind of like the floor planning of it or the massing approach to it. And that way, once they take these colorful images, they can sort of modify it to generate like a 3D object that matches to some sort of floor plan that they're sort of looking to optimize. This other work is by Casey Ram, Co-Intelligent Machines. And what he's doing is he's using STYLEGAN in this case, training a whole bunch of architectural images. Once he has these, let's say, generated architectural images, he translates them through some voxelization style method into like a 3D object. In a more sort of pragmatic approach, I would say, the use of reinforcement learning by Pedro Veloso. It's in this project called the Academy of Spatial Agents. So in this case, Pedro's essentially having multi-agents learn how to plan spaces by themselves through a set of strict rules and rewards. And on a given site, they're able to essentially learn from their interaction and generate these spaces of varying square footage and connections. So all these spaces are interconnected, but they have a variety of different, let's say, areas, which is very interesting. So this shows the possibility of being able to use reinforcement learning for space planning. In this work by Andrew Witt, Formaps, he's using computer vision to be able to catalog floor plans from the city. So by taking, let's say, the floor plan of a whole bunch of buildings in the city, he's able to generate these sort of like tree maps of similarity. And this is a very interesting approach in the sense that it sort of uses the machine to do some kind of analysis and understanding in a historical matter of what the site looks like, or what the sort of types of forms that are being produced in a real urban environment are, and how they fit together in some sort of connection to each other. In this work by Daniel Bulajan and Deep Himmelblau, he trained STYLEGAN of all of Coop Himmelblau's projects. And then by doing this, he's able to generate pretty much architecture similar in the style of Coop Himmelblau, which is very interesting. So this is an approach of using STYLEGAN to generate something based on a data set that he fed into it. In this project, Large City Architecture by Daniel Kohler and Rasa, they use reinforcement learning to be able to generate these sort of structures. And it obviously has some constraints in the sense that some of these structures are generated based on like the walk-in distance, and like if you have to have some sort of connection between different floor levels and what is like the maximum walk-in distance that you can have. And based on that, they can generate like these platforms and grow this three-dimensional building. In this project, Artificial Remnants by Sofia Crespo, she uses generative networks trained on bug data, and then also a corpus of descriptions of animals and bugs. And then what she was doing essentially is generating new, let's say, bugs or creatures, and then generating their description based on trained data. So she takes a new created bug and then feeds that image of a newly created bug through some sort of model that takes the image and generates text from it and generates a description. So this is kind of like a very interesting approach that it combines two parts, the image generation and then the text generation, to create like a whole new object. In this work, House Yan++ by Nelson and team, they use generated networks to take, let's say, the graph of a building, or like a building design, like if you have like different programmatic spaces, and to be able to generate and produce new floor plans. And then as more recently, Theodore Galanos has used DALL-E to train on 150K images with text of house floor plans, and they're color coded based on the program, let's say. And then based on that, he's able to generate using text different floor plans. And this is some of the work that I've done using STYLEGAN and converting that style, let's say, newly generated objects into like 3D point clouds. So you can, I trained this on this is from Flickr images, train them on 2,500 Flickr images, and generated new images based on that original data set. Once that data set was generated, then we would take that and input it into another neural network that predicts depth maps. And then those depth maps get converted into point clouds to generate these 3D objects on the right side. This is another project that I worked on, which uses reinforcement learning to pretty much take, let's say, modular units and learn how to rearrange them in a very unitized manner. So it's very voxelized in the sense where like each unit is a 10 by 10 by 10 cube, but they have different, let's say, architectural components like walls, roof, ceilings, or columns, and the algorithm learns how to like connect them in a way that the floor plan allows some flow through and that it's able to stand. In a more recent project that I worked on with Victor and Tanya at a cadre workshop, we used some computer vision algorithms and connected them to like urban data, where we got some scraped images from Google Earth of the site in Brisbane. And once we have those images, they get fed into a computer vision algorithm that segments them. And we're able to take those segmentations and apply some more mathematical formulas to calculate certain, let's say, features or numbers out of that correlate to the idea that we were pursuing, as to understand like what features in the urban streetscape relate to a change in prices in real estate. And here you can kind of see like certain images represent different clusters or features in certain areas. And those are correlated to like the prices to those areas. And another project that I worked on, which uses CycleGAN to map images to images, and StyleGAN. I was able to get a whole bunch of images scraped from Instagram of different types, and then pair them together using CycleGAN. Once that pair happens, it generates like a new image. And then when we take that new images, those new images, we're able to, let's say, generate them in a three-dimensional way and see what comes out of it. And this was a more experimental approach to see if we can generate some sort of three-dimensional architectural sections based on those combinations. What was interesting about this approach is that you want to take sort of unrelated images and see if you can generate novel, let's say, images based on those two, let's say, pairings. And as more recently, this is more or less something more similar to what we're going to do in this workshop, which essentially using a VQ GAN and clip, we're going to take text to generate images from that text, or guide a VQ GAN to generate a certain type of images. And then once we take those images, we can then come and produce a three-dimensional space out of it by running it through another network that can project a depth maps. Okay, and that's all I have for now. So hope you guys like that. And if you have any questions, let me know. Thank you.
Thanks, Daniel. I feel it was like a crash course of AI for architecture, where we covered like from beginner models to like state of the art. And I'm pretty sure like few of the models which were released like few months ago. So great presentation.
Yeah. Thank you.
Any questions from the participants? You can also ask like if any of his project which you would like to know more about the models or post-production. Cool. So one thing I'd like to share is like, if I were in your shoes and if I'm just starting out, it might feel like an information overload with like so many models, so many data types covered. So one advice I have is, depending on your topic of research or area of exploration, you will select a particular model, and then you might need to build expertise and knowledge in that area. even in computer science, there are like people solely working on text models. There are people solely working on computer vision models. So it's a lot of things in to cover in like from vision to language and like multimodal. So a few examples I can think of is, let's say if you are doing a precedent study, or if you want to do like a literature study of brutalist architecture and you have a text corpus, maybe you can use transformer model to create novel essays. Or if you like, Ricardo developed a app where he was using different architecture styles and did classification of those architecture styles. So you might use like a CNN based architecture to do that and do labeling for that purposes. And if you feel you want to make a generative design of flow plan or rendering, you might be interested to look deeper into GAN types of network, which are mostly interpolatory, where based on the particular theme, you can generate novel themes. Like there are a lot of models which Daniel covered. So depending on your intent, like we saw like text to text, image to image, but also multimodal, which converts text to image or image to text. So it's a whole another field where there are like you get novel surprises and creativity, where you see a museum designed by Zaha and you find few aspect of Zaha's parametric style and also few surprises by the machine. And it's, yeah, you will notice by end of second or third day when you start exploring that.
Yeah, the most
I'm-
important part is to experiment.
I'm going to make
Yeah,
a
go ahead.
question about the Viki again. It's like DALI is not open source yet, right? It's from OpenAI, and I think we can't use their model yet, right? Am I
You
right?
can use it. No, you can use it, but it's not like you're able to like train on top of it. You can sort of run through their let's say like if you want to like download it from GitHub, you can like run through their train model and like use that, which is in a way kind of like how we use Clip. And one of the reasons why is because like OpenAI has crazy amounts of resources. So they train like the Clip model on millions and millions and millions of like images and text that, you know, for like if you want to train it on your own, like it's going to take a while and you probably need like some time, and you want to have like as, you know, as much GPUs as they did to be able to get like a pretty let's say good results. So that's kind of like one of the reasons. But there's been efforts on I don't know if you're familiar, on GitHub, that people have tried to let's say like reconstruct like DALI.
Because so they're like, they share it, the method of training, but they did not share the model they train it, right? Because I saw this community trying to like replicate the results, and it's very interesting, but we're still not far yet. In my vision, from what I understand right now, I think that like the Vikigan and the Clip is like what we have closer to DALI to use now, right? It's like what tools we have available, right? So this was what I was trying to understand. Okay, but that's it.
Yeah, VQGAN comes from another paper called Taming Transformers, and they also have like a trained VQGAN. But the reason why I guess it's become more popular is that because it has, let's say, like it's less parameters, so it's less computationally intensive, so you can run like on Colab much easier. You can also run DALI, but you would have to like, you know, you would just use their sort of pre-trained model as well. But you have, I think, a little bit more flexibility in terms of computational efficiency if you want to train on your own, like your own VQGAN.
Thanks.
There are few trained DALI models, like on the link I shared in the chat, where like, because ultimately what we are doing is we're using Clip to direct the image generation. So you could use like a noise generator or a GAN or DALI or VQ GAN with Clip to generate like text to images. Any questions?
I kind of had a question. So previously I was reading about the house GAN plus plus, wherein it is a GAN to help in floor planning and internal organization. So I was wondering if graph neural networks could be used for floor planning, because in the examples that you showed, it was primarily for predicting proteins and something associated with biology. So I was wondering if it has been previously done, GNNs for floor planning, or any references that you might share be helpful.
Yeah, actually, house GAN plus plus uses graph plus GAN.
Yeah.
Okay. Yeah, I wasn't aware. Thank you.
Yeah, no problem. But that's a good thinking that, like, if you have room-wise relationship, maybe graph neural network is more suitable compared to GAN. So I think that kind of thinking you're developing it, you're in the right direction.
Yeah, thank you.
Cool. If you have any questions, you can type it in the chat, but we will take should we take like 5 or 10 minutes break? Okay, let's do 10 minutes, and whatever, depending on your times, and you can have water, tea, coffee, and we can jump back in.